Okay, so it's exactly 10:30 a.m. Let's go ahead and start. Good morning, everyone. Welcome to our live webinar hosted by DKSH Technology Malaysia. Hope everyone is well and safe. Thank you for joining us in today's webinar. My name is Lidu and I'm the marketing representative at DKSH Technology Malaysia. We at DKSH Technology are a total solution provider in scientific instrumentation, precision machinery, and textile machinery. As a total solution provider and system integrator, we serve our customers as a one-stop shop and provide customized technology solutions. At DKSH, we support our customers throughout the entire product lifecycle, from sales to after-sales service, including installation and commissioning, final acceptance testing, production startup support, training, maintenance, repair, spare parts and consumable supply, as well as refurbishments and trade-ins. So today we'll explore the topic of tips and tricks for fast GC analysis presented by Dr. Jet Yu. Dr. Jet Yu obtained his PhD degree majored in analytical chemistry from National University of Singapore in 2007. He has published a couple of peer-reviewed papers specialized in chromatography method development. After graduation, Dr. Yu joined Johnson & Johnson Asia Pacific as senior scientist for the discovery of skincare products and has filed 2 proprietary patents as key inventor. Dr. Jet Yu joined TechCom Singapore in 2013 as a product manager, overseeing analytical instrument products in the region. Currently, he's a regional manager for the sales and business development of cyan chromatography products in ASEAN and South of Asia. Before we dive into this webinar, if you have any questions during the presentation, please type them into the Q&A section on the right-hand corner of the screen, and they'll be answered at the end of the presentation. Now, without further ado, we'll turn the time over to our presenter, Dr. Jet Yu.
Thanks, Lidu. Good morning, everyone. Last webinar, we talked about the troubleshooting of the GC peaks. So today I'm going to talk about the tips and tricks for the fast GC analysis. Okay, so why do fast GC analysis? Basically, it is a matter of time and money. All right, so you can also say it's about like efficiency. So the benefits are pretty obvious. So first of all, the costs can be decreased. If you have the shorter analysis time, of course you can do more analysis within a day. Okay, and also some of you can share the same machines, so it's more like a utilization of the systems. Okay, second one is revenue can be increased. This is like more for some professional testing labs. Of course, they want to have one capital instrument, they can do more tests, they can charge more, okay, make more money. All right, so basically the fast GC analysis can be applied to any applications with no sacrifice in quality. So what that mean? So basically, if you have any type of applications, there's always a way to improve the GC to shorten the analysis times, okay, by means of method development or optimizations, okay, without sacrifice of the resolution. So last one also is quite important, because when we have some requirement, usually we say, oh, do we have to add this or add that, which is the additional cost. But for fast GC analysis, there's no any additional equipment. It's purely on the method development. So all these benefits, to drive many of the users to looking for the faster GC analysis. Okay, so basically compared to conventional GC analysis, fast GC analysis typically is 3 to 10 times faster. So it depends on the applications. Whether your existing analysis is complicated or relatively simple, then you can define how much faster we can do. All right. Okay, so anyway, however, before you do any quick or fast analysis, there's still a couple of questions you have to ask yourself, because personally, I think there's no absolute fast. So not all the applications need fast analysis. Okay, so this is a key point you need to be aware. So first of all, why do you need a fast GC analysis? Okay, as what I mentioned, not all the applications you can have very fast analysis. Some of the analysis you maybe improve a little bit, some you can improve a lot. So This is the question you have to ask. Second, how fast do you expect? This is usually compared to your existing testings. All right, there's no absolute fast. To some of you, maybe 30 minutes is already fast. But some of you may, oh, I want 10 minutes or even 5 minutes. Okay, also could be 1 minute, or could be 1 minute, all possible. But so there's no absolute fast to all applications. Okay, so before you have such type of like request, you have to compare, have to look at existing or current analysis time. Example, you already have a GC analysis methodologies with like 60 minutes. Yeah, 60 minutes is, to me, for separation techniques, it's pretty long. All right, so 60 minutes. So your working hour is 8 hours. Okay, or some of you may work overnight, or may just stay late in the lab. So anyhow, let's say 10 hours, so including the lunchtime, whatever. So if you have 1 hour, 1 hour analysis time per run, you can only run how many examples? 10, which is not so much, not so many analysis in a day. And plus, you also still need to have some preparation and also conditioning this timings. So it's so 60 minutes is really long. So you are looking for a faster GC analysis to improve your efficiency. Yeah, that sounds reasonable. Okay, but if you already have 10 minutes, then you want to shorten to like example 5 minutes. So then you have to think about it. It's really worth, to looking to developing such a method or not. Okay, but 10 minutes anyhow is already short enough to me. Okay, maybe to most of you. So you have to think about this before you have this type of mindset. Although I want to have very fast analysis. Okay, so next one is what information do you need? Okay, so when you are pursue fast analysis, you are going to lose something. Okay, so this is you have to make sure what information do you need. Some of you may need like a qualitative analysis information, but some of you also want both quantitative or both. All right, so you have to make sure what exact information do you need. Yeah, this is also important. Do you need to resolve all the components? When example comes, there's a number of components in the examples. Okay, but you have to make sure what is your target compounds, because this is able to help to develop the method. If you tell me I want to resolve all of the components, then it is going to be struggling to develop such so-called fast GC analysis, because you have to consider the separation of all the components from very beginning to the last eluters. Okay, so if you only target like those later eluters, then probably it's more easier, it's more doable for you to develop such a method, because you don't have to care about the rest. You only target those target compounds you want to analyze. All right, so you also have to make sure, yeah, what exactly do you need. All right, and also, is there enough baselines in between those peaks? When two peaks, those peaks already close to each other, which means it is more difficult to develop shorter GC analysis within short times. Okay, because all those peaks already close by. So if you shorten, then the resolution is going to be worse. All right, so maybe example from 1 reduced to 0.8 in terms of the peak resolutions. All right, so this is a few questions are more details, but overall the benefits is there. All right, efficiency can be improved overall. Basically, there's a couple of principles for fast GC analysis, total 6. All right, so first of all, I think if you have like a suitable stationary phase, so which is a coating inside the columns, so this is more related to the selection. Okay, and also column oven for GC, and also carrier gas is also important as a column itself in terms of the length, ID, and also the film thickness. So total 6 principles. But you have to manipulate all these 6 factors in order to achieve fast GC analysis, because you are going to manage between those speed, resolution, and the capacity. All right, you cannot simply pursue the speed, then you lost the resolution. Okay, you can also simply pursue the resolutions, then the time is longer. All right, also capacity, this is about the sample loadings. All right, if you choose a narrow ID columns, you just can able to load less samples into columns. Then this is more about the sensitivity issues. So you have to balance these 3 the factors by manipulating these 6 principles. All right, so you can look at these. There's a multiple factors, which means the method development is more tough, more struggling. So there are 6 variables you need to manage. Okay. So before we talk about each one, I have to deliver some information to you about this rotation time and the resolution. So this is the 2 formulas I have to discuss today. Otherwise, you are not able to understand the relationships among those factors. Okay. So the first one is rotation time. All right. So you look at this formula. So you can, I believe most of you already are aware of this, how to do. So rotation time. So for fast GC analysis, so the shorter rotation time, so the faster. Okay. So you look at these variables. L is the column length. Yeah, I think this one is more straightforward. Shorten the column. Yeah, reduce the analysis times. Okay. K is the rotation factors. So this is more about the interaction between the analyzed and the spatial phase. All right. So if there's a strong retentions, so those compounds is going to stay in the column for a longer time. Okay. End of the day, it's a long analysis. Okay. So another one is carrier gas. Yeah, this is also one of the key issues. The carrier gas is a mobile phase. Whether you choose the faster carrier gas or lower carrier gas, direct link to the the total analysis times. All right. Later on, we will cover each of these factors. So all right. So in generally to shorten analysis time, you need to use shorter columns. Okay. Choose high linear velocity carrier gas. All right. There's a couple of carrier gas I think you are familiar: nitrogen, helium, hydrogen. So which is the fastest? Hydrogen. All right. But there are some concerns using hydrogen. Later I will cover this. And also the need to increase the oven ramped rate, so the temperature. So if you are having higher temperature in the GC ovens, so all the components intend to elute out faster, okay, which is able to shorten the analysis time. Okay. So next one is about the resolution. Okay. So the first one is the time. Of course, the shorter the better. All right. But we are not able to consider this rotation time only. We also have to think about the resolution, because for modern separation techniques, separation is the first. Without the separation, without the proper separation, whatever, how fast, how slow the analysis time is, no use. So separation is the first. So with this condition, then you can go and pursue the shorter analysis time to improve the efficiency. All right. So this formula comes, show here is pretty complicated and longer. There's also multiple factors here. So the first one is the N. N is the theoretical plate. All right, it's more about efficiency. Yeah, basically this is a number. This is the variables to show you how efficiency your current methodology is. All right. So you see, if in order to achieve higher efficiency of the separation, you see there's a couple of factors also here hidden inside. So gas is more about the carrier gas. All right, length. RC is the radius of the columns. All right. So the idea of the columns. So You see, for n, there's a couple of variables inside. Okay, so this is a way how to get a number of the n theoretical plates. So basically, at peak, you have the half width and you have the rotation time. Then based on this formula, you're able to figure out the n. Okay, so just now I will show you the formulas of the TR rotation time formulas. Then see in between inside this TR, so there's multiple factors. So you have to manipulate this, the rotation time, column length, carrier gas, and also the column ID. So next one is the K. K is basically the retention factors. All right. So this is more about the stationary phase. How strong the retention for analyte inside the columns. So it is a matter of temperature, T for temperature. DF is the film thickness. RC means the radius of columns. Okay. So this is a way how you define the retention factors. Retention time minus T0. 0 basically is air peaks, okay? There's no retention at all, okay, as a reference. Then you divide by these numbers, you get the retention factors. So different component has a different retention factors, okay? So like temperature-wise, if you increase the temperature overall, then the retention factor is less. So the alpha is a selectivity. Okay, so this is more related to the interaction between the analytes and the stationary phase. Okay, so if there's no stationary phase inside the columns, there's no any rotation selectivity at all. So all the peaks, all the components will elude as a single peak, right? So when it is important you choose the right phases. So later I will cover. So basically the principle to choose the right phase is based on the principles the like dissolves the like. This is more from the chemical properties. So polar likes polar, non-polar likes non-polars, but non-polar doesn't like a polar. Okay, just like a water and oil, they are not able to be mixed, which means there's no any interaction in between. So different components have a different interaction with the stationary phase. That's why you can see the separation. All right. So components 1 have one retention time, component 2 has another retention times. Because each molecule has their unique chemical properties. So the polarity is different. So stationary is a phase, but the analytes, all the analytes have different polarities, which means the interaction between the three phases are different. This is the reason this is the reason behind you're able to see the separation of the peaks. Okay, so if these two peaks they have very close or similar, chemical properties, then there's difficulties in separation. Then we have to modify how we achieve, how to separate these two close property components. Very simple examples like isomers. Isomers they have same molecular structures. No, they have same molecular weight. They have similar structures. So it'd be difficult in terms of separations. Okay, so based on these, you're able to get the resolutions overall. So you have to manipulate all these. So retention alpha, they are more close to the retention times. All right, retention time, and the factors all inside, hidden inside the formulas. Okay, so first of all, I would like to more talk about the phase, stationary phase. So there are a couple of stationary phase. This is, I think, the first key step for you to start a GC analysis when you have certain target compounds you to analyze. As what I mentioned just now, so the principle to choose a phase is based on the chemical properties, like dissolves alike. So the common stationary phase will be like xylazine polymers. So this is a common one. So the code of the column, I think you often see is 1535. Okay, so this column is more like a non-polar, based on these polymers. So the phase is based on these polymers. So this is non-polar. All right. So if less numbers, so naturally it's more like a non-polar in your phase. So when you have of course, when you have like some oil examples, yeah, you better choose this non-polar columns. For like hydrocarbons, yeah, you more choose this type of columns. Okay, so the next one will be called like a PEG. So this is more polar stationary phase. So usually the column code will comes like a wax. Okay, wax. The sound is our sound GC, column, brand name. Okay, usually this dash, this one, similar whatever from Shimano, Agilent come with the wax. So this is for polar. So you look at this polymers, there's a hydroxy, groups. So this is very polar groups. If there's water, so there's hydrogen bonding in between. So this is a very polar, polar compounds. Okay, station phase. So example, you want to analyze the alcohol. Yeah, you intend to choose this type of station phase because alcohol is a very polar compounds. All right, another type of station phase is porous polymers. So there's sizes in between the layers. So which has larger surface areas. All right, generally there's a three typical solution phase, which defines the selectivity. So just now I already mentioned selectivity is more about the spacing in between the peaks. All right, so different analytes have different interactions between the solution phase. So which is really depends on how the difference is. Then for the GC to separate these target components. Examples, when examples in is come as a mixture. So this is compounds A, this compounds B. This part is a stationary phase. So obviously the red dot has more strong interactions. Okay, because this direction is example out. So this is circle, white circles, which has less interaction between the solution phase. So somebody pull you behind. Okay, when you are running, somebody pull you back. See how's the force of the pulling back. All right. So obviously this white compounds will elude out first, and the red one has a more higher affinity to the stationary phase. So this is a general way how the separation is going on inside the columns. Okay, so look at these examples. The first one we are using Cyan 1. So just I mentioned Cyan 1 is non-polar columns. Okay, so you look at the chromatograms. So there's a total 13 minutes. Okay, so if you are satisfied with the 13 minutes, okay, go ahead. So you don't have to spend time developing method because the method development is really time consuming. Also, you need to have the the mindset in mind what to change in order to shorten the time. And some of the peaks have like separation issues. Okay, so then we switch to wax columns. So this is polar. Okay, polar columns, stationary phase, which means this type of compounds are more polar. All right, then you change to the different column. You change a little bit about the the oven ramp temperatures programs. Then you're able to separate all of them within 5 minutes. Okay, so from 14 minutes to 5 minutes is almost 2 times faster. All right, so this is a pretty good examples. So for any of you who want to develop methodologies, fast GC analysis, so you have to, the column is one of the things you have to start with, think about. You have the compounds to be analyzed in hand, then you have to think about which type of columns you need to choose. Okay, because once you install the column, then you're able to modify, optimize other factors in order to achieve the fast analysis. Otherwise, it will start from the very beginning. Okay, so column length is very straightforward. You shorten the columns, then you are able to have faster times. So relationship is the resolution is linked to the square of the theoretical plate, and also accordingly, the square of the length. Okay, so it's not like you increase 2 times the column length, you have 2 times better. No. So if you have like 4 times column length, then you only improve the resolution for 2 times. So vice versa, if you shorten the column for 4 times, also you should reduce the resolutions accordingly. All right. So look at the relationship between the lens and the spherical plate. This is straightforward. If you increase the length, then the theoretical plate numbers also doubled. All right. So look at these revised examples from 60 meters, 30 meters, 50 meters. So the resolution is reduced from 1.6. So usually resolution equals 1, which means it is baseline resolved. So this is usually one of the standard we acquire when it comes to the resolutions. But for this type of resolution, we're also able to accept, it's not baseline resolved, but I think the resolution still is able, based on the calculations, about like reach to 1.1 something. Okay, but come to this one, maybe it's only 0.8. This is not able to accept. Okay, so when you do the quantitative analysis, it's going to be like not accurate. So basically, when you do the peak splitting, then the area may be not that accurate. Okay, at this too. Okay, so you have to think about which type of resolution factors you are satisfied. So usually this type of the middle one, this type of resolution is okay. It's good enough. Okay, it's very close to baseline resolved, but not like this. So another benefit of reduced column is, the cost. Okay, the column for some type of column is not cheap, right? So you reduce the columns, of course, it's cheaper. Column ID, so you see, look at this. I think the most common one is 0.53, 0.32, and 0.25. Come to narrow one, 0.1. So these are a couple of ID columns are available for user to choose. So you look at the efficiencies. So the N, the theoretical plate numbers, the higher the better, because this is about the separation efficiency. So look at, you see when the column ID is reduced, so the efficiency is improved. So naturally, if you choose smaller ID, it is better to achieve the separations. In the meantime, it's highly possible to achieve faster analysis. Okay. So also you look at this right two photos. The first one is like HETP. So HETP stands for high equivalent of a theoretical plate. So this number, the lower the better. Okay, because you see, look at the formula. This is the plate numbers. This is the column length. So this is the HETP. So for HETP, the numbers, the less, the higher the efficiency of the serial numbers. Okay, so you look at this photos. Obviously, when you choose a narrow ID, you have the lower HETP, which means you have higher efficiency. Okay. Also look at this one. So this y-axis also is HETP, and this one is carrier gas. All right, together with the ID. So carrier gas, I will explain more in later slides. So look at this. When you choose a narrow ID 0.1 and hydrogen as a carrier gas, so you have the highest, you have the lowest HETP. So as a result, it's the highest efficiency of N. Okay. So usually there's a couple of this type of photos available, curves available for user reference when they are going to pursue fast analysis, and you can use this type of curves as reference. At least you have the directions. Oh, this is the way, this is the direction I have to follow in order to achieve fast analysis. Okay, so this is one example how when we reducing the column ID and able to achieve fast analysis. Okay, so the first one, conventional methodologies, usually we use 30 mm and 0.25 ID and 0.25 film thickness. So this is a very common one. All right. So for this compounds, you're able to achieve separate all of them within 26 minutes. So 26 minutes is depend on the users. I believe most of you still will feel this is too long. All right. Yeah, 26. Personally, to me, also a bit long in terms of time. So 30 minutes, then it's one cycle plus conditioning. End of the day, so one run is able to take about like 45 minutes. So this is a bit long. All right. So within a day, you are not able to run a lot. Okay, unless you run the overnight, you create a sequence, you run the overnight. That's okay. So usually like less than 15 minutes is acceptable for most of the users. All right. So we switch to these conditions. So 10 mm or 10 meters. Well, this is 1/3 shorter, 1/3 of this first one. ID 0.1 and also film thickness 0.1. All right. So basically, basically when you change the column length and the column ID and the film thickness will also be changed in the same time. Okay. It's seldom you just shorten the column, then while you didn't change, while the rest two factors remain unchanged. Usually they are changing, they will change at the same time in order to achieve much faster analysis or much better efficiency. Okay. So come to film thickness. So this is another key point. So once you, as what I mentioned from the very beginning, so film thickness, the type of column is also one of the key. Once you are clear with the properties of your compounds of your target, and also you're able to choose film types, station phase types, and also the thickness. Okay, so this is a column actually I amplified to show how the column is, what they look like in terms of the design, coatings. So the out layer is a polyimide coatings, so the golden yellow one. So this is a polyimide coatings, which provides the mechanical strength. So without this coating, the column is easy to be broken because the material is the column wall is a silica. Okay, silica is broken, it's very easy broken, very weak mechanical strength. So without this polyimide coatings, then it's a bigger problem. Okay, so with the coatings, you're able to circles and bend the columns without much issues. Okay, so the red part is a stationary phase. So this is a coating. All right, homogeneous coatings along the columns. So I zoom in part of the field. Okay, then we see this red part. Basically, red part is a stationary phase. Okay, it's a fixed. So basically, the triangles and the green part is the analytes and the carrier gas. So under carrier gas, so the example actually is moving along the columns. Basically, this is a dynamic, a balance equilibrium. So the stationary phase, is constantly, dissolve the analytes. In the meantime, release the analytes. Okay. So the example actually they move in one direction. All right. So it's not like the stationary phase catch the analytes and don't let go. No. So if you don't let it go, which means the retention is really strong, all right, then you can expect how long it will take for the compounds to leak out from the columns. Okay, so by considering the properties of the analyte phase and also analysis time, so you have to think about this. So this is a dynamic equilibrium. Okay, the analytes keep interacting between with the stationary phase and while continuously moving out through the columns. Okay, so you look at these relationships. So if the film thickness and also retention change, so you see there's the really significant in terms of the percentage. All right. So usually when you choose the narrow ID and the shorter columns, then the film thickness also need to be reduced accordingly. Okay, and because when you are choosing the narrow ID columns, then the production manufacturing of the columns is more difficult because narrow ID and they need to pump some of the polymers through the columns and dry the polymers before deliver to customers. Okay, and from manufacturing production wise, it's more difficult. So there's less. Yeah, vanilla ID. So the solution is not easy to pass through. Okay. All right. So look at the below chromatographs. You see when you reduce the column film thickness from 1.0 all the way to 0.25. Then you look at the times. We should target this one. 30.2 minutes, 7.4, and 4.7. Okay. So you can achieve the faster analysis in a significant way. All right. So you just look at this rotation change. So this is in terms of the percentage. So this is really significant when you change the film thickness. All right. So I would also like to talk about this phase ratios, which is important. So just now I mentioned, usually when you change the column length, film thickness, ID, so this few factor actually are changed the same time. But there's one factor, they remain same. So we call phase ratios. So what does that mean? So phase ratio is defined by the radius divided by 2 times and the film thickness of the film. Okay. So yeah, sometimes also it's ID. ID means times 2, and also here times 2 becomes 4. So this is a column ID. I is a radius. All right. This is a film thickness. So this is the way how we define. So the phase ratio usually remains the same when you transfer from one condition to another. All right. So examples. So this is a 2 column dimension before and after you change. You see, look at the phase ratios, it can maintain the same, 44. So which means the efficiency usually remains the same. So 0.53 is the ID. Okay. So you calculate 0.53 divided by 4, then divided by these numbers. So these are 44, the phase ratios. Okay, so this is a reference, so guidelines for you to work with. So usually, as I mentioned, these two are changed at the same time in order to maintain the same phase ratios. Okay, so by this way, you will have like a shortcut to have quick condition change from one to another. Okay. So there are some this kind of our references for users. So you have to be clear about the direction. So direction is more important. If you go to the wrong direction, then you're going to be struggling all the days. Oh, how come it's really there's no any clues to achieve the short analysis times? So another key factor is the temperature. Yeah. So in the GC, the temperature is very important. So when you increase the temperatures, so the viscosity of the mobile phase becomes less. Okay. So when you think about the oil, so when you put into the cooking, when you're cooking your oil, at beginning very sticky at room temperatures, right? So when you heat up, so it's more like mobile. It can flow very easily. So this is inside this, reason is because of viscosity. Viscosity less, then they are able to move much faster. So temperature is applied to all to the entire, will affect the entire analysis from very beginning to end. Okay. In generally, you increase the temperature, so the analysis is also faster. Okay, much faster. All right. Then you are also able to achieve fast analysis, but of course, behind the change of temperature, you have to think about the resolutions. Okay. So usually the temperature change we will modify from the middle afterwards. Okay, because the very beginning this temperature is already quite low. All right, when you start a GC analysis, this is about the temperature gradient. So usually the initial temperature is low, and the before end of the oven programs, temperature programs, the temperature getting higher and higher. Okay, so it will generate great impact on those late eluters. Okay, late eluters they intend to stay in the column, not willing to not going to come out very fast, but you increase the temperature, then you can able to help elute faster. Okay, then reduce the total analysis times. Okay, you look at these chromatograms. Here we just simply change the the temperature programs. Okay, so this is initial one, so the run time is 24 minutes. You look at those elute columns. So this only 4 peaks. Then they still far away. Okay, far away means there's less risky for you to come across the separation issues. They are still far away. Okay, then why not you increase the temperature after this point? Okay, you increase the temperature of the GC ovens, so you're able to help to elute these 4 peaks faster. All right, so we increase the temperature RAM rate from 5 degree to 10. So the by end of the program is about 192. See, from 23 minutes, it was shortened to like 15 minutes. But you look at these peaks, still far away. All right, and the peaks are very sharp and still far away. So the spacing between these peaks there's still sufficient room for you to shorten the times by changing the temperatures. Okay. Then we increase to 15 degree per minute. This is a ramp, okay, rate. All right, so from the 15 minutes again, you reduce to 12 minutes. All right, but you look at this 4, but still, the peaks still are far away with each other. But I show you, this is just examples. When it comes to 12 minutes, if you are satisfied enough, then we can stop here. Yeah, personally, I think you less than 15 minutes. This is good enough. All right. So very obvious. That's why when you have a request to achieve for faster GC analysis, you have to study your chromatogram first, see whether there are any possibilities in improve to shorten the times. But some of you may think, oh, why not we start from here? Yes. So there's a spacing here. But however, because once you change the temp conditions over here, then you are able to affect the rest. So you think about this. But here you look at this. This is a few peaks, no issues. You look at these 2. So these 2 peaks, so it's close by. Okay. It's already close nearby. I think this is the resolution is about like a 1.2 something. Okay. You think about these 2. All right. If you change the condition over here, and then it may affect the separation of these 2 peaks. All right. So this is very important. The start point where you should start to change the conditions without affect the rest. Okay. So this is very important. Otherwise, you just spoil the whole chromatograms. Then you have to start over again. Rather than you're struggling on the shorten the time, then you are struggling on the separations. Okay. So if you are mixing these 2 together, then you are going to spend more times on the condition optimizations. Okay. But if you just want to make these 4 components a little faster, then it's easy. From this point, after these 2 peaks, just increase the ramp. So these 4 peaks will come out very fast. Okay. So make it like a 10 minutes or 12 minutes, which you are satisfied. All right. But rather than you start from beginning. So okay. So this is very risky. If you change from very beginning, this is going to affect the entire chromatograms. Okay, the elution orders and the resolutions as well. So it's more like struggling for you. Okay, so next key factor will be the carrier gas. Okay, carrier gas. So the common one will be helium, nitrogen, hydrogen. Okay, just now I mentioned the viscosity. You look at this y-axis stand for viscosity, and this one x is stand for temperatures. So you look at these 3 curves. So which has the lowest viscosity? Hydrogen. So just now I mentioned the lower the viscosity the carrier gas is, the faster the GC analysis. Okay, so this is one directions for you to choose. But there's some other, factors for you to choose in terms of the cost, safety. Then I will cover in the next slide. Okay, and come to the, the separation efficiency. Then usually we look at this, so-called Van der Meter curves. Okay, this is more related to the separation efficiency. This is only for which is faster, but faster doesn't mean, you have the good efficiencies or resolutions. So this is a more often common one for user to turn to, okay? Because the Y stands for height, which means the theoretical plate. But the lower the better, okay? The lower the higher the theoretical numbers, okay? Don't this is you have to be clear, okay? Not the higher the better. This is the H is the lower the better. So the X stands for velocity, okay? OPGV, optimum practical gas velocity. Okay, so usually you can say it's a working velocity. All right. So you look at this three. So in order to have the same efficiency, so which carrier gas has the highest velocity? So obviously it's a hydrogen, right? In order to achieve the same efficiency for nitrogen, you just need to have like a 15 cm per second. Velocity is the distance traveled for a gas. Okay, it's not flow rate. All right, it's because flow rate also, you have to consider about the diameters, ID of the columns. All right, so usually this is velocity, which means the distance traveled within a second. All right, so for nitrogen, you need to set around like a 15, but probably plus minus. But this is a working range for nitrogen gas. If you have higher, more than like a 20, then the separation efficiency is reduced. Okay, this is not the direction we want to see. Okay, we always want to have the highest efficiency, but the faster. All right. So you look at the helium. Helium is better than nitrogen. All right. So it's a 25. So this range 25 plus minus. Okay. So this bottom areas is a working range for the helium as a carrier gas. The faster, right? It's 2 times. But you look at the hydrogen, even faster. All right. So you see, even you increase the hydrogen, this is optimum 40, but you can able to increase up to 50, but without much sacrifice of the efficiencies. Okay. So based on we leave other factors aside, based on these curves, so hydrogen is the best. So you think about the GC, you have to change the column, carrier gas. So if your lab is allowed to use the hydrogen, then probably you need to, have the GC setup with the hydrogen gas. All right. Maybe one GC with a common, if you have multiple GC, maybe one GC hydrogen, another GC nitrogen, another GC maybe helium. Okay. Depending on the needs of the applications. All right. So this is the guidelines. All right. You look at this. Yeah, this is straightforward. Just a change from the carrier gas. From the nitrogen 15 cm, velocity, helium 30, hydrogen 47. All right. You look at this, and the time is really shortened a lot. All right. So without change any other conditions. So to develop a fast analysis, I think from very beginning you have to think about the carrier gas. Okay. So of course, the hydrogen has other concerns in terms of safety. All right. So better efficiency, more separation at higher gas velocities, and also improve the column lifetime. Okay. And then less column bleed. Bleed is natural degradation of the cellular phase released into the carrier gas. All right, and the less temperature required, and the cost effective. Yeah, hydrogen compared to the helium is cheaper. The helium is more expensive. All right, but hydrogen you can use the hydrogen generators. So there's more like those options available for user to choose. But the key concern for hydrogen is safety. So till today, still many of the users still reluctant to use hydrogen based on the because hydrogen is really explosive gas. Okay, so the gas leaking because it's not like a liquid. Liquid you are able to see visibly, right? As any leaking from the syringe, from the gas bubble is able to see. The gas is invisible. All right, unless there are some, if that's especially the minor gas leaks, you are not able to perceive even from the sensors. Okay, and you are not able to see. And okay, you look at these numbers. Basically, for the lowest exposed limit is about 4%. Basically, it's pretty this limit is pretty high enough, pretty high, which means it's not that easy for the explosion to happen in a lab. Okay, with the minor leakings, it's not possible because there's a minor leakings. Sometimes you are able to perceive how come the baseline not stable and the repeatability not good. Then you start go and check the hydrogen unless there's very serious leakings. So this is another story. Okay, but in modern times, but GC already comes with many safety measures in terms of the software and hardware. All right, for some GC, from the software and hardware, it's already we already adopt these key safety measures. So if there's any leaking of the carrier gas, automatic shutdown. All right, and also the GC main box. Basically, for some GC, it is ATEX certified. So what that mean? So even inside of GC got explosion, so the flame still maintained intact. Okay, there's no flying pieces. Look at the past. World War the war. The fightings. Actually the killing piece. The killing part is the flying pieces. The bullet. Okay, the bomb. Okay, the flying pieces. So this is the key, because the flying pieces fly all the directions. So this is the way to get people, injured or hurt. Okay, the flying pieces. So even this is the main box. Even inside got explosion, the flame still maintain intact. So this is, I think, one of the criteria for ATEX certified. So this is from the hardware. This is safety. Second one, I think most of you are aware, this is more about hydrogen sensors. Yeah, this is more important. When there's a leaking, the software is able to tell you, oh, there's a leaking errors. Okay, so this is able for user to be aware and shut down the carrier gas and check the connections. All right. So basically, this is sensors installed in the apartment, and this part is a probe to the column ovens. Okay, usually the column connecting broken or connecting not good, or leaking in the ovens. All right. So the sensor usually come as a bundle, and the one controller actually you can connect to 4 sensors input. And this is a sensor and also some electrical gas sampling valves. So this is all like software controlled. So you can connect to 1 GC, 2 GC, and even 4 GC with one sensors controller. All right. So from the software, hardware, I think there should be less concerns in terms of safety for user, because in terms of the efficiency and the fast, hydrogen is really the best carrier gas. All right. This is more similar like last time, like peak troubleshootings, like some software translators for you to work with, like when you transfer from one method to another. So basically, you can use this online free software to do some calculations. Right, able to see, oh, how much faster I'm able to achieve. Okay, by changing these conditions, column length. You see the phase ratios as here. Velocities, all these. This is the calculations. So this is original method, 36 minutes. Once you change the conditions, you reduce to 12.7 minutes. you look at the speed, it's a 2.8 faster. Okay, so this is free online software. You can visit anytime you do these calculations before you change the method. Okay, so keep in mind when you do something, conditionally optimized, you can refer to this, free softwares, and the previously those curves I presented and showed to you. You can at least you need to have very clear directions to go with. Okay, then it will take you, a shorter time to optimize the conditions rather than struggling, today you change it, tomorrow change it without any guidelines. So this is more struggling for you. Okay, so this is all very useful, this type of like a software for you to optimize the method in order to achieve fast analysis. Okay, so as a summary, so this multiple principles, you have to think about these multiple principles before you optimize the method. Stationary phase, okay, chosen for optimized selectivity. All right, so we have to be clear with the chemical properties of your examples. Okay, whether it's a polar, middle polar, and non-polar. All right, if you are not clear, you can Google and search for the information of the compounds. Okay, generally when there's a number of hydroxy group, OH group, so this is polar. All right, this is very polar. Come to the oils, this is non-polar. All right, think about this. Yeah, smaller ID allows a shorter columns but less capacities. Okay, smaller ID and less film thickness and shorter columns, because this you have to change these few factors before you transfer from one method to another. All right, but it's less capacities. So what I mean, when you choose a smaller column ID columns, so the loading amount need to be reduced, but this will be reduced, will be relevant to the sensitivity. So if your example already have like a target compound already have very less concentrations close to detection limit of FID or TCD, but do you think it is worth going for faster? Not really, right? Because in this point of view, sensitivity is the most important. Because if you are not able to detect your target compounds, there's no point to develop a fast analysis. Okay, think about this. So this is only the points I need to highlight. It's less capacity, which means the loading amount is less because the column ID is very narrow. All right. So the carrier gas, yeah. So hydrogen is the best, but depends when it comes to the GCMS. All right. So for FID, TCD, these common detectors, hydrogen is the best. But come to GCMS, it will be different story, because this is more related to chemical inert of the carrier gas. So for GCMS, helium is the best one because helium is the most inert. All right. So temperature in general, the higher oven temperature ramps helps to reduce the analysis time. Okay. And the ramp. So ramp is another different story compared to the temperature. Temperature is the overall temperature range, but ramp is how fast the temperature increased. So just now there was examples. So for the later eluters, if the spacing among these peaks still sufficient, then you are able to have a higher flow rates in order to make those late eluters come out faster. Okay. So this is a general guidelines for you to work with. Okay, so I think that's all for today's talk. Hope it helpful. Hope it is helpful for you to daily works in the GC analysis. Thank you. So now we now to Q&A question sessions.
Okay, thank you for your presentation, Dr. Jett. Now let's go ahead and take some time for questions. Feel free to drop your questions in the Q&A section and then we can bring it up. The Q&A section is on the right-hand corner of your screen, so please feel free to drop your questions there. So we'll give about 5 minutes for the questions to come in, and then after that, we'll wrap up this session. Okay, so we have the first question in.
Okay.
Dr. Jett, can you go back to slide with right phase and explain for mixture with polar and non-polar compounds, what phase should we choose?
Okay. The mix, right? This one, right? Can you see this one, right?
Yes. Yeah,
Okay.
that's the one.
All right, let me close this one. Okay. So yeah, the key, the first step to start with analysis is the spatial phase of the columns, because this is the core of the separation. Without the right, the spatial phase, you are not able to separate your target compounds. So yeah, the principle is like dissolves like. Okay. So when there's a polar compounds, then you need to choose polar stationary phase. Okay, so this is between the chemical interaction in between. All right. So the stationary phase, this is really a typical stationary phase. So this is non-polar. So you look at these chemical groups. This is alkane groups. So this is a non-polar. This interaction is based on the covalent bondings. Okay. Example, this is stationary phase. Another compounds also have a similar chemical groups. Okay, so their interaction is covalent bondings. Okay, they share electrons, so this we call covalent bondings. All right. So this one is polar stationary phase. So you look at the chemical group is OH. OH. This is a very polar groups because the hydrogen bonding is possible. So when you come with another compound like OH, right? So there's a chemical hydrogen bonding in between. So hydrogen bonding is a very, very strong interaction force in between, chemical force in between. All right, just like water. Why water stay as a water? Because there's a hydrogen bonding in between. Because the water molecule is O2H. Okay, so the O will in interaction with the H from another molecules, then the H will will be interacting with another molecules, water molecules, with the oxygen. Okay, OH is a very strong bondings, hydrogen bonding in between. So this is interaction. But when you come with the example, this is a stationary phase, then you come with this type of non-polar groups. Do you think there's interaction? No, there's no interaction between. Or you can say there's very weak interaction in between. So in this means when your mix is all have the similar chemical properties, which means if all these two are non-polar, then you choose the polar interface, stationary phase. Then this two is not going to be separate from each other. Okay. Because these two molecules, they're in native, they are different in terms of properties. Because there's no absolute non-polar, there's a relative. Oh, okay, maybe this one I'm more like polar than you. Okay, this analyte is more polar than this one. But overall, these two are polar compounds. So we are not talking about absolute polar, non-polar. We are talking about the relative. So this is This is a native of the separation. So the difference in terms of polarity is very weak. Okay, sometimes we from the molecular we are not able to tell. Okay, but from these separation technologies we are able to differentiate. Oh, this one is a polar than this one, or this one is polar than this one, depending on the elution sequence. Okay, so here we don't know which type of station phase they are using, but we know their relative affinity to the stationary phase. Okay, so this is more like a this is a matter of resolving interactions between the analyte and stationary phase. Okay. So is that clear? Did I answer your questions? So
Okay.
it's more about the force in between.
Dr. Jet, so the same person is asking if my compound suspected to be a mixture of both. And then the next question is from the same person: will a highly polar compound retain permanently in column and cause contamination or drop in performance of column?
The polar component permanently stay in the column.
Okay.
So this is less likely for the components to stay in the column. Okay, because this is dynamic, equilibriums. So it's not like I capture you, then you stay with me, or please don't leave. No. So the carrier gas is there. Okay, the carrier gas is pushing the analytes throughout the columns. Okay, so let's say this is a very polar stationary phase, right? And you come as a very polar analytes. So naturally, it has strong retentions. So it will come out in the last minute, but doesn't mean it will stay in the columns forever. Okay, because with the carrier gas there, carrier gas actually supplies the continuous force to push the analytes throughout the column. Okay.
Okay, hope that question is answered. Okay, so we'll just give about a minute. Okay, so from the same person, there's another question, which is Scion -1 and -35. What does the higher number mean?
Okay, for -1, right? So this is a stationary phase. So this is a polymers, okay? 100% is a polymers. Well, 5% means there's a few of the groups are modified with the different compounds. So which means the overall properties were changed. 5% of for different compounds, okay, replace these chemical groups. This 5% or 35% may be more polar. That's why we are talking about the columns. There's highly polar columns. There's mid-polar columns, okay, and there's less polar columns all the way to non-polar. So the modification of this type of groups is able to help to tune the polarity of the columns, which can entertain different versatile compounds, right? So the -1 is 100% polymers of this one, all right? No modifications. 5% and the 35%. Let's say this 35% is more polar, okay? So which means this stationary phase, right? Maybe it's a half polar, half non-polar. We call it mid-polar columns. So these columns, suitable for those compounds which have like a mid-polar polarities. Is it clear? So just now I'm talking about the 100%, either highly polar or highly non-polar. But there are some compounds in between, right? Middle polar. All right. So these are the number means, okay. But usually type 1 and the type 5 columns can be applied for, I would say, to 80 to 90% of applications. Okay. And the rest of the 10, maybe you need to choose the right columns with the different numbers. But you have to look at the chemicals, what's the properties of those modified part, 35 or 5. Okay, I just list two. There's other numbers like 1701 and 624. So there's guidelines in the some website. Then you are able to tell, oh, this is the direction. This is a column that I should go with. Okay, there's introduction in the brochures for you to tell or which type of columns for you to go with. Like alcohols, obviously this wax column is recommended for you to choose because alcohol is a highly polar column, highly polar compounds. So the same scenario actually applied to the HPLC as well. Yeah, because this is all separation, technologies. This is all about the interaction between the analyzed and the stationary phase. Okay, so you have to think about from the chemical property perspective. Then you are able to choose the right stationary phase columns for your analysis. I hope it answers your questions.
Yes, okay. So I think with this, we will wrap our session. Dr. Jett, is there anything you would like to cover before wrap up?
Yeah, I think the more or less I cover all the key factors.
Okay.
Of those principles. So as what I mentioned, you have to refer to these curves before you start to change your method, change your conditions. Okay, so this all give you the some guidelines for you to start with. Okay, and yeah, just think about this first before you start. All right, so actually this is my advice for all of you. It's not that easy because there's so many factors, variables there for you to consider. Okay, it's not like a single variables. It's about 5 or 6. If you look into these factors, actually there's some more hidden behind. Basically, these are general guidelines for you to think about with. If you are from the testing labs, so you more think about the revenues, right, in terms of the cost, and also your charge to the customers. Okay, if you have very efficiency methodologies, you are able to get in the 10 minutes, you will charge cheaper. Example, and then you also have advantage over competitors. From your research perspectives, I think the start points are different, but you are more think about maybe the resolutions, okay, separations rather than the time. Okay, you will not struggling of like 5 minutes difference. Okay, but you would rather focusing on the separations and the resolutions. All right, and the safety is another concern. If your lab have a serious safety concerns about hydrogen use, then you better switch to others. Okay, so these are all multiple factors behind for you to start with. Okay, so I think the different users, they have different scenarios, so you have to think about this. I think I think these few factors already cover all the concerns you have. All right, I think that's all. Yeah.
Okay. Okay, so with this, let's end the webinar. If you have any questions, feel free to drop an email to marketing.tech@dksh.com. Thank you all for joining in today's webinar. We hope you found this webinar very informative, and we look forward to having you in future webinars. Stay safe and take care.
Thank you.
Thank you, Dr. Jett.